If we're looking at this question, we should start at the same place we start kind of all questions. And depending on kind of the format of that question, it changes a little bit. So we could say, what's the most reactive thing, or what do you see? Okay, so what you're trying to do is identify any piece of information that you can navigate from or with. Okay, since we're given a reaction, I would argue you should start what's the most reactive thing you see. Okay, that question is very specifically asking you to look for that Cario scheme that we talk about, where we start at charge, then size, electronegativity, resonance, all that fun stuff. Because that's going to help signal where our chemistry's got to happen. So what we should be able to do is look at those structures, okay, and if we're not given structures, imagine those structures or draw those structures and try and highlight the chemistry associated with them. Okay, Cl2 is for sure written out as a formula, so we could redraw that one. So we see that a little bit more explicitly as a molecule. The sodium hydroxide, hopefully what you would do is zero in on this and say sodium hydroxide is my most reactive thing. And that's because when I look at sodium hydroxide and looking at the bond connectivity there, the bond between the sodium and the oxygen is an ionic bond. And since it is an ionic bond, that is best represented, shouldn't have erased the sodium, as a positive and a negative. So when we're now going through and looking at our whole system, we've got reactivity. Sodium as a metal, all OChem, so pretty much you can take in all scenarios and just toss the metals aside and ignore them, okay, at least in their ionic form, which means we're looking at hydroxides. The most reactive thing we've got is a negative oxygen. Okay. As a negative, what could it act as? A nucleophile or a base. Okay, so pulling that content back up to help. Right? If it's going to act as a nucleophile, what do we need to find? We need to find an electrophile. What is an electrophile? A positively charged atom. So we can go through and look at all these pieces and be like, I don't see anything positive, okay, right off the bat. But then what we should be going through and doing is looking for those further breakdowns. For instance, that first structure, we have a pi bond. That pi bond should set us up with the potential for resonance. Okay, and what we're drawing out is our useful structure. The structure that was initially given was our best resonance structure. But if we look to the useful one, that helps us to see some of the chemistry, and in particular the chemistry that it points out is that I have a positive carbon. So I can say, oh, okay, there's a positive. Okay, I don't need to look at the chlorine because I have a formal positive now. So I could have my negative oxygen come in and share with that carbon. The context of this particular reaction as we're drawing it right here, and if you're copying, please stop, sets us up, there's our negative, green, and there's our OH. Based off the lecture that we just had on Tuesday, we should have some information about this. So we go through and look at that, and we say, what have we formed?
Was it the hemi-acetyl?
Okay. You could put this in the acetyl family. Acetal family. Sorry. This isn't technically an acetal. It isn't a hemiacetal. It's a hydrate. Okay? As long as you're saying anything within that family, though, that's probably good enough. Because within that family, what do we know about the stability of this structure? It's not. This goes backwards. Okay? So yes, we found a positive, but that positive isn't going to react in a favorable way with our oxygen. It's going to form an unstable acetal family structure that's going to revert backwards. So we would need to find a positive somewhere else. This is where things can get kind of content-wise tricky, or you have to kind of use a little bit more imagination behind this. Nucleophile or base. If hydroxide is going to act as a base, what do we need to find? An acidic hydrogen. We would need to find a hydrogen. Oh, we've got a hydrogen drawn. Is that hydrogen acidic? Okay. The aldehyde hydrogen is always going to stand out there. It's almost always drawn on, and it's drawn on almost universally as a trap. Okay. For students to meet, oh, that's the acidic hydrogen. It is not acidic. Okay. You can go back to OChem 1 or talk to me in class, OChem 1 lectures, okay, and address that. The acidic hydrogen is going to be at the alpha position to our carbonyl. Why is that alpha position acidic? If I go through and remove that hydrogen, why is that more acidic than if I picked off, say, the red hydrogen? Fair play, didn't consider the proximity to the oxygen. So we've got an inductive effect that we can, I would argue, cheat with and say that the red hydrogen is not as acidic because of induction. The green hydrogen, or the one that we're showing as the green structure, is more acidic because it's closer to the oxygen. But more importantly, what could it do? We have that resonance stabilization. That resonance stabilization should set us up to see a couple things. Number one, probably most relevant, okay, that's why that hydrogen is acidic. Okay? What else is that hydrogen doing being acidic? It's stabilizing that positive charge. That positive charge that we acknowledged at the very beginning was reactive. This hydrogen is acidic because it's stabilizing that positive charge. It's all part of the same connectivity. So if we recognize that initial resonance, that could help us out. If we're going through and looking at the successful direction, so this was unsuccessful, this was unsuccessful, our green arrow is our one successful case, we could go through and decide, well, how is that structure now going to go through and react? Okay, well, we've got two resonance structures that are drawn out. One of which, the first one, and our setup, we should acknowledge is awful. Why is it awful? Lots of charge. Yeah, lots of charge is a bad idea. Okay, you can lean on it even further. We're looking at a missing octet. The other structure is better because it has all of its octets. Is there another resonance structure that I should be considering? Yes. Okay. So if we were going to go through and label these, we have awful, okay, because of all that charge. In between green and purple, which one's better?
Green.
Green, because oxygen's more electronegative. You're using your charge size electronegativity rule set to explain why it is best. Okay? If I now want to say, how does this chemical reaction continue? Because at this point, I still haven't addressed the chlorine in the reaction. Should I be using my best drawing? No. The best drawing is the most stable. It's the one least likely to react. What I should be using is the first worst, or the first awful, because I wrote awful up there, which would actually be referring to the purple structure. That purple structure we've been calling useful. Okay? The best structure doesn't give me the chemistry. The purple one gives me the useful. What does that mean as far as utility? Well, what's the reactivity on that purple structure? Say again? I have awesome, overwhelming confidence. We have a negative charge. That negative charge could act as a nucleophile. It could also act as a base. Is it going to be useful to act as a base? No, why not? That just goes backwards. You mean this is an equilibrium reaction? Yeah, it is an equilibrium reaction. Right? So I don't like the base chemistry. I want it to act as a nucleophile. If it's going to act as a nucleophile, what do I need to find? I need to find an electrophile. So I'd go back to all of my reagents and say, do I have an electrophile? Well, the hydroxide we called as a nucleophile or base, so that's out. We did reference the carbonyl as potentially acting as an electrophile, right? But we reacted that one. It could theoretically double back and react with itself. Okay? What else have I left off other than all these hydrogens?
Chlorine. Yeah.
I ignored the chlorine. Is that chlorine an electrophile?
Can be. It splits up.
Okay? And this becomes one of the challenging questions because we initially look at that chlorine and say, oh, tons of electrons. Tons of electrons means nucleophile or base. It's not a nucleophile or base. Those chlorines cannot donate those electrons in any real extent. The only way they could donate those electrons is once that bond was broken. Is that bond likely to break? Well, chlorine elements are electronegative, which means they're pulling on those electrons really, really heavily. And if, say, a nucleophile got close to one side of this, that's going to cause that to pop. That pop sets us up with a new structure. Kind of make sense? Right. Within this approach, what we tried to do was just what's the chemistry we see? What's the chemistry we see? Not only what's the chemistry we see, but we tried a whole bunch of different chemistries, and those different chemistries resulted in horrible products. You need to do that. You need to see those dead ends and be comfortable recognizing that, yes, that's a dead end, I need to do something else. Right? Because if you don't do those wrong things, what's going to end up happening is you will discover on the exam when you will do all the wrong things, and that's going to be then. That's when it's going to count. Right now, it doesn't hurt to do wrong things. It spends a little bit of time, but hopefully it gets you the answer. So we go, cool, we finished this, I now have a neutral structure. Of course, I can now enter this into SmartWork, and of course, SmartWork comes back and tells us we're wrong. Right? Why would it tell us we're wrong? Right? So to help with that, or hurt with that, what are we going to do? We're going to delete everything. And this becomes yet another thing that pops up in kind of OChem 2 that we have to be aware of. When we go through and run this reaction, we have hundreds, thousands, billions of these molecules. So the reaction runs once, and we produce this. Right? So now in solution, all of those materials are there. Every single one of them. Product and the starting materials. What's the most reactive thing? It's still the hydroxide. Hydroxide is still there, which means it is still active. It is still there as a negative charge. What do we need to do? It has to act as a nucleophile or a base. We tried it acting as a nucleophile, and what happened? It went bad. That was a bad idea. So it doesn't act as a nucleophile, it needs to act as a base. And if it's going to act as a base, what is it going to react with? It's going to react with an acidic hydrogen. Where are there acidic hydrogens? Well, one of the things that I happened to memorize was the carbonyl. The carbon next to it has acidic hydrogens. So ta-da, there's acidic hydrogen. Oh, it's boring. That just gives me the same product. True, but what else is also present right now? The product. That product that I've drawn out also has a hydrogen there. Between green and red, which one's more acidic?
Red.
The red one's more acidic. Which means when the hydroxide comes in to run this reaction, okay, for the second cycle, if you will, what's it going to react with? It's going to react with the red hydrogen. We just erased everything, but what do? All that same stuff that you did, you do again. And that red hydrogen is now going to be converted into another chlorine. So the reactions run twice. So now all of these things are present. All right, we could say it even ran 3 times so that we actually have this molecule still present too. What does the hydroxide react with now? Well, I screwed up the first time. I'm not going to let that happen again. It must react with my product, so it's going to pull the hydrogen off of my product. Where's the acidic hydrogen in my final product? It isn't there. Which means, what does the base react with? It could react with that intermediate product to make my final product. It could react with the starting material to make the intermediate. But ultimately, all that's going to end up happening is everything is eventually going to siphon across to become that final product. There's no more reactions that our hydroxide can go through and do, which means that's where we end, and that's our final answer. Okay? Ways or things that we could add to our list of how we want to memorize this, basic conditions, you don't get to stop. Okay? If we're going to run this, the base is going to constantly deprotonate, and anytime there's an alpha hydrogen, I'm going to replace it with a halogen. Not chlorine, but a halogen. Because I could add Br2, I could add I2. Probably wouldn't add F2 because it would explode. Okay? But I could add any one of those things. That's not changing the inherent chemistry of the halogen compound. And so it should continue to react as much as possible. Does that mean your answer is going to be the one with all of those alpha hydrogens replaced with chlorines? Maybe. If it's multiple choice, look at your multiple choice answers. Maybe they decided to just do it once and they threw in chlorines at all the other spots just to test. Do you understand which hydrogen is the acidic hydrogen? Okay, so depending on what you're being asked and what your answer choices are, you can change kind of where your response is going to go. Does that make sense? Okay, so base. I need to do full substitution with all of my alpha hydrogens as much as possible.
So instead of a hydrogen on the left, what if there was a methyl? Would that, all get turned to chlorine, and would it leave?
So, and this is where we hit a weird gray area. So what Andrew's asking is, what if we made this a CH3? So first and foremost, what do you think should change? Okay, we have more alpha positions. Those more alpha positions are now active. Those more alpha positions should go through and run the chemical reaction. Okay? Which means we should theoretically see that CH3 disappear. And I'm just going to draw it as this. Those had 3 hydrogens. We could put those in as chlorines, because those are all alpha hydrogens. Should we also go through and attack over here?
Yes.
Well, those are also alpha hydrogens. Couldn't those also theoretically run? Yes, they can theoretically run, but we encounter kind of a weird gray area in this space. Okay? That gray area is that once we've done that 3 substitutions, those chlorines are bugging me. And if they're bugging me, it's not even a question for y'all. Okay? That is actually, whoa, what is my screen doing? A decent leaving group. Okay? So hydroxide could now come in and act as a nucleophile. And if we look at the product of that, what do we get? I drew them nice once. That's all I need. All right, we could argue, oh, we're in this weird hemiacetal type thing, and it's unstable and it should fall apart. Okay, it's technically even more unstable than that. Okay, so we would want the electrons to come back down to reform the carbonyl, but now we have an interesting dilemma. What do we kick out? Hydroxide or this CCl3 thing. The CCl3 thing is a decent leaving group, which means that can get kicked out. Why does this become important to us? If we do that, what we end with is the carboxylic acid. Not just a carbonyl anymore, but a carboxylic acid. Does that change my chemistry? Yeah, it's going to change a lot of chemistry. Okay? How stressed should you be about this extra step, per Andrew's question? It is a gray area, unfortunately, for this particular unit, because the reaction we just did, this blue arrow, is what kind of a mechanistic step?
Nucleophile addition.
Try again. That's a nucleophile elimination. What reaction have we, or mechanism have we been studying this unit?
Nucleophile addition.
Nucleophile addition. This is unit 2. That's everything that we've been addressing. This extra step here, nucleophile elimination, is unit 3. So this extra step isn't technically this unit. So could it show up on the test? Yeah. Why? Because we've talked about it. We've now talked about it multiple times for this particular reaction. Would I expect you to do nucleophile eliminations that you haven't seen before? No, because we haven't talked about those. But have you seen this one? Yes. So you should be able to do this one. Okay? How many times do you think I should ask a question about it? Okay. Is this worth it to you to memorize that one step for one question? And that is a rhetorical question. You get to decide. Do you think I'm going to ask that one question where I have the methyl ketone, ACH3, next to the carbonyl? Then memorize it. Turns into a carboxylic acid. Done. When it shows up, yep, that's what it is. Circle the answer and move on. Okay? If you don't think it's worth it, then don't memorize it and hope you don't see it. Because doing all of that mechanistic details is a stretch at this point. Because again, you just barely been introduced to the nucleophile elimination. You don't have a lot of practice with it. Does that kind of make sense? We got a couple questions, one from Megan and then one from me. Go ahead.
So how do you know which way to go with it?
So deciding which direction, which hydrogens you should get rid of goes all the way back up to the beginning. Whoops. With our very first structure, how do we know we should get rid of the red hydrogens versus the green hydrogens? Right? You tell me. Why should we get rid of one versus the other? Accessibility, which is a fancy way of saying kinetic versus thermodynamic. Okay. In this case, that reaction happens fast enough that when we form the kinetic enolate, okay, it can react with chlorine quickly enough that we start doing that substitution. And so we see the kinetic product carry through. Okay, and we don't see the thermodynamic product, which is interesting considering that hydroxide should favor the thermodynamic product. But if we look at those cases where we're favoring the thermodynamic product, we aren't reacting it with something as active as chlorine. Okay? So the presence of the chlorine is what's actually allowing the kinetic to get stuck in the kinetic path. Kind of make sense? Okay. But I would argue you have another follow-up, right? That follow-up, let's go to the product. Aren't those green hydrogens still there? Couldn't those be removed by our base and continue to do the substitution? Of course they could, Mike. Could they? Why were the hydrogens being removed? They were more acidic, right? Is there a more acidic hydrogen in that final product? Yes, where is it? The carboxylic acid. That hydrogen's more acidic. Okay, so the base removes that one. Fine, I still have base. Can it go after the green ones? This is where it's going to come down to, is it acidic enough? Okay? In our top case, where we ran through and did all those continued reactions, okay, was there any extra thing that I needed to factor in? no, the product had an inductive effect and that's why it was more acidic. But if we double back and now look at this final product, let's say our base comes in, removes that hydrogen. Are those green hydrogens acidic? For them to be acidic, what has to be true? Conjugate base must be more stable. Do I have resonance for that conjugate base? Can't I do resonance to stabilize it? Yeah. But what is different about this product that we didn't get with all the other ones?
Two negatives.
A couple big pieces come into play. Number one, I've got two negatives in this structure now. Two negatives is not particularly stable. I'm creating a very unstable structure by having the double negative charge. Okay? So using charge right out of the gate should scream it, you don't remove those green hydrogens because that makes an incredibly unstable structure. Okay? Fantastic site. Didn't even consider that. My bad. I should have seen that because charge is more important. What else could we have seen? What is that negative oxygen capable of doing? Resonance inwards to stabilize that positive charge, thereby preventing the other carbon from sharing electrons inwards. We're getting competing resonance. Both of those things and charge, most importantly, would suggest this structure is not good, which means it goes back to our starting material, which means once I've made the carboxylic acid, do I get to continue to do substitution on those hydrogens? No. Neat. You opened that can of worms, not me, for the record. Guess where we start? Unit 3. That exact question. Because Unit 3 now says, okay, I've got a carboxylic acid. What can I do that chemistry? No, you can't. We can't because that functionality here, the carboxylate, stabilizes the positive carbon so much that we effectively get no chemistry centered at that site. We lose it altogether. Okay, Unit 3. Before we continue to fall down that rabbit hole. Oh, okay, fine.
So,
Where are we going,
what's
Alice?
the point of it saying excess CO2? Why doesn't it say excess NaOH? Because isn't there like millions of molecules or whatever?
So I would argue, so this is push through. Is the base catalyst? I don't think the base. I undid all my mechanism. Because the base does not act as a catalyst, is actually acting as a reagent here. Why they didn't say excess sodium hydroxide, I don't have an answer for. Why did they say excess chlorine? Because they were trying to be nice. They were trying to help you say, hey, you should keep going. Okay. They didn't need to say excess because it was naturally going to go already because those hydrogens were more acidic. Other questions?
In the second intermediate or the first intermediate, what's to stop the sodium hydroxide from doing a substitution to chlorine?
Let me erase to make sure I know what you're talking about.
The middle one.
I'm going to try and set up some of this. So you're saying here, why can't the hydroxide just act as a nucleophile?
So make it unstable.
you're going to end up with what I would classify as a pseudo hemiacetal. It's not called that, but that's how I would look at that chemistry.
Positive carbons and two.
If you put a chlorine there and an OH there.
No, wait, can it take the chlorine?
Oh, whoops, sorry. That's right, because you were doing the substitution. So it's not the semi-acetal argument. I think what you'd be pushing is a steric argument, because you're trying to run a backside attack on that site. And it's going to be easier to remove that hydrogen than it is going to be to do that substitution. With the oxygen there, you're still generating a partial positive carbon. So I believe that's what you were talking about. But then you're saying it wasn't partially positive up here. It's a larger positive after the substitution. But yeah, I think it's going to be a steric argument, or potentially, which is a nasty response, it didn't do it. So we're just pretending and saying we aren't concerned about it. Okay? A proper physical chemist would be like, well, why did it not do it? Let's look at the energetics behind each of those systems and try and evaluate that. Unfortunately, that's not me. So, for this particular question, what's our answer? Red box. We good? Okay. So just to be nice to people at home, we'll kind of talk through some of this. So everybody's got answers up on the board and got at least structure A down. So that's good. But again, what I want you to pay attention to is your process. What are you trying to go through and do? So in some cases, we had people immediately drawing structures, okay, drawing out chemical reactions. In other cases, we had people summarizing the spectral data. In other cases, we had people actually drawing spectra. Okay? All of those are valid tactics to go through and take. What you're trying to do is get the language away from the language and get it into organic chemistry language, the structure stuff that allows you to interpret and navigate. Right? And if you're going through this question being like, well, dang, I didn't know 7.15 ppms meant aromatic ring. Okay? For the sake of the homework, that's okay. But that should now be something that you're acknowledging that I have a gap in my understanding. That should be on a memorization list. You should have a secondary sheet of paper with you whenever you solve these questions. Be like, I missed this. I didn't know this. Put that down on that list so that when it gets time for the exam, you can review that and be like, dang, that's something I'm going to need. Okay? Or, as I talked with someone else about, I don't know anything about spectroscopy. I don't remember anything about it. Okay, is your choice going to be that you're going to ignore it? That's fine. You can make that choice. But then that also means when you get to a question on the exam with spectroscopy, what do you need to do? Move on. Don't sit there and stare at a question that you've already committed to not answering. You're wasting your time. Okay? And everybody will sit there and stare at it. I hope something just comes to me. And it's fine to do that. At the end of the exam, after you've put down all the answers that you already knew, then you can go back and just stare at it and hope for divine intervention. That's okay. Okay? But don't do that early in the exam. Constantly advance through and move on. So within this, things that I would do personally would probably be start to underline things. So 7 ppms tells me I have an aromatic ring. 3 tells me a question mark, personally. Right? If we're going through, we could use the sheet that I've given you in the past, but that's where I would go. I've got a 5-to-2 ratio. Ooh, that gives me a little bit more information. That means probably on my aromatic ring, I have 3 hydrogens, and then I've got my question mark next to it, which probably has 2 hydrogens on it. That would give me my 5-to-2 ratio. Okay, the IR spectrum has no absorption in the 3200 to 4000 range, which is really just a fancy way of telling me no OH. Okay, and then it gives me strong peaks near 1700. What does 1700 mean? Carbon, oxygen, double bond. Okay, I already started to process some pieces together. That carbon-oxygen double bond can't be question mark because that would exceed its octet, which means if I'm going to build this out a little bit further, all that information gets me to, oh, where am I at? Attempting to color code. Carbon, oxygen, oh, dang. I've got another hanging bond out there. If I put another hydrogen there, that would show up in my HNMR. I wasn't told that I had that. How can I address that? So there's something else going on out there. I don't know what that is right away. Okay? Depending on your comfort with this, you might go, well, whatever it is, I have to put something there, but it can't affect the other chemistry. Okay? I can't add more hydrogen. So I could do a halogen. Okay? That's not going to change my hydrogen signals. So hey, maybe that works. Okay? After that, it's saying this is all compound A, so now I have a structure for compound A. Compound A reacts with sodium borohydride to produce compound B. Okay? It also says an acid workup, which is nice. So we got 1, 2. Sodium borohydride gives me H minus. Acidification gives me H plus, so I have a negative and a positive in my overall reaction. So I go back and look at my structure. I have a negative and a positive, right, due to that carbonyl. So I could go through and drop hydrogens on it. But if I dropped hydrogens on it, then I've got this bromine chilling out there. Like, what functional group is that? Silence is actually a pretty good response to that. Because what functional group is that? A new one that you haven't studied yet, because that's unit 3. Right? So if I'm going to try and run a chemical reaction with this, do you think it's reasonable that I threw a question at you where you had no context of how that reagent would react? Sometimes, maybe. Okay, but that seems a little sketchy. So maybe it's not bromine, because I don't know how that would chemically react. I know I'm looking at polar pi bonds and their reactivities, and we're focused primarily on aldehydes and ketones. It can't be an aldehyde, so it has to be a ketone, but a ketone is going to bring in more hydrogens. But could I bring hydrogens in such a way that I don't bring in new hydrogens? Yeah, if we duplicate. Okay. If I duplicate, I'm mirrored across this, and so I don't have any new hydrogens. They're duplicated on the other side, which means if I now go through and look at it, it's technically 10 to 4, but a 10 to 4 ratio is 5 to 2, and that's exactly what my spectra told me. In all of this interpretation that I just went through and did, some of you might be saying in the back of your head, but Mike, you didn't look at the formula. Yeah, I just happened to realize that. By the way, bromine makes absolutely no frickin' sense because bromine's not in my formula. Right? But that's one of my personal weaknesses. I tend to ignore formulas. Because I ignored that piece of information, I had to rely on other context to help build that out. But if we look to that formula could have helped us to see that we needed to duplicate out. That context gets me structure A in reality. I now could start to take my H minus and my H plus. I take the negative, put it to the positive. I take the positive, to take it to the negative. And I get structure B. Okay? I'm not going to draw that one, make you do a little bit of work. What happens with C? We'll see, we take that same structure. I'm going to abbreviate now. Phenyl, carbonyl, phenyl. And we react it with CH3 MgBr and then acidification. I had one person, oh, I know H plus. That H plus is going to have to end up at the oxygen. Yeah, that's true. Okay, that's arguably jumping steps. Okay, and if we did that, we got those electrons probably from the pi bond, which means that carbon would be positive. What would I need to react with that positive?
Negative.
And because I have an ionic bond, because I've got magnesium as a metal, I know that carbon is a negative. I just drop the CH3 into that spot, and I now have that answer. You don't have to follow a mechanism through this. You can follow the charges and start placing those pieces. Right? Giant text bomb of a question can be simplified as long as you start taking those steps to put that information down. Okay? For the sake of everybody at home, whoever happens to go back and watch this video, you all took a real long time to get started. There was a lot of staring at the question, I don't know what to write, I don't know what to write, I don't know what to write. Okay? Until I pointed out the two groups that started to write something, and then everybody started to write. Okay? As long as you start putting something down, you've started that interpretation process. Even if it's repeating the information. But even in your repetitions, you didn't write the HNMR spectrum of compound blah, blah, blah. You just said compound A formula. There's a lot of extraneous information that you can get rid of. And once you get rid of that and strip it away, you can start to solve. Much like all of my lectures, right? You can ignore half the words I say and you're still successful. Or all of them in some people's cases. Since Tyler's so far behind his lecture watching. Make sense? Okay. Yeah, that was the button I wanted to push. Cool. So here you go. New question, 10 minutes. You got boards. Okay, you can erase the stuff that you put up there, or you can just start finding a new white space. Start working with what you see, and just start trying to make progress. This is not a simple reaction. There's a whole crap ton with it. How do we know there's a whole crap ton with this chemical reaction? If we scroll up to the actual text, the text says Robinson annulation, as in this is a named reaction. Why do we name reactions?
They're weird.
Because they're weird. There's a lot going on in this reaction. As soon as you see a name, that should start to incite a little bit of panic. Okay? Which means navigate, and as you navigate through, look for things that you might be like, but why would it do that? But why would it do that? This is the last one in Carbonyl Additions Advanced. I think it's the last one. It's for sure it's question 11. And I think everybody has the same one. I don't think there's different ones. We got a lot of different things going on behind this. And please pack up. We're at 43 minutes, so if you want to, when you get home, you can just advance to 43 minutes whenever I get the lecture up. I'll try and get it up today. Okay, KOH is our most reactive, our most acidic hydrogen's in there. That most acidic hydrogen is going to get removed, and we're going to end up forming a negative charge on that carbon. That negative charge is now a nucleophile. We need to find an electrophile. If we go through and look at the other side, we're going to encounter a problem. We have two electrophiles. Okay, we have the electrophile coming directly out of that carbonyl due to the resonance, but because we have a conjugated system with that pi bond, we'll also find we have an electrophile out there. So we're looking at the two possible resonances where the negative charge is always going to be on the oxygen. We'll color code a little bit here. If we look at the green one, we'd be adding a negative and a positive, or adding to those negatives and positives right next to each other. Let's say oxygen special is carbon number or atom number 1, which means when I add another atom to that carbon, I would get a 1,2 reaction. If I did it with the purple one, it's still going to be the negative oxygen, so it's still position 1. Where's that purple positive? 1, 2, 3, 4. We're looking at 1, 2 versus 1, 4. If we added some extra words behind this, this would be a 1-4 conjugate addition versus a 1-2 direct addition. Okay? The extra words that go with these, if we're looking at a direct addition, we're talking about the kinetic product. If we're looking at the 1-4, we're talking about the thermodynamic product. How do we decide between kinetic and thermodynamic products? It has to do with reversibility of the kinetic step. Okay? If your reaction is irreversible, your kinetic one, you get the kinetic product. If your kinetic one is reversible, you get the thermodynamic product. So what you would need to do is look at the nucleophile strength and decide, where does it rank? Does it rank as a reversible or an irreversible nucleophile? To decide that difference, that's again comparing stabilities of those individual ions. Grignard reactions, those were irreversible, negative carbons. Okay? Hydride reactions, irreversible, negative carbons. Hydroxide, reversible. Okay? So we could group by the atom charge. If we go through and look at the nucleophile we're talking about in this reaction, what do we have as a nucleophile? After our acid-base reaction, we have a negative carbon. Since it's a negative carbon, we would say irreversible. And unfortunately, we're wrong. And the reason we're wrong is, what are we looking at when we look at this red structure? Which resonance structure did we just look at? We looked at the useful one. And if we're going to try and predict something about its chemistry, what do we got to look at? The best. And when we draw out the best resonance structure, what are we going to see? Negative charge on the oxygen. What did we say oxygen was? Reversible. We're going to get a 1-4 conjugate addition. So our nucleophile is going to come in and attack at that purple carbocation, not carbocation, but that purple positive. It's going to go through and do that normal addition process. You're going to run a whole bunch of mechanical stuff at the end of that. You'll be like, hooray, I'm done. And it's going to tell you you're wrong. Okay? And it's going to tell you you're wrong. Why? Because it's the Robinson annulation, and you got to do more work. Okay? That more work has to do with evaluating the strengths of our acids and bases within solution, and are there ways that we could stabilize a big floppy chain? Make a ring. Okay? So if we're looking beginning to end for the Robinson annulation, if named reactions, if I'm correct, it is a Michael addition, which we just talked through. That's the 1-4 conjugate addition, followed by an aldol condensation. I'm probably going to butcher the structure of the product, but I'm going to give it an attempt. Oh, I should not attempt this. Oh, I should really not attempt this. Okay, there's there. Call that a dot. We've got an ethyl carbonyl there. Phenyl carbonyl. Okay, and you might wonder, why did I draw it in such a way? I drew it in such a way, that's the Michael addition. I drew it in that way so that I could see the ring close. Any idea where the ring's going to close?
Oxygen.
What happens when you combine red and blue? You'll get a purple structure. Huh? See? Phenyl. And when we talk about the aldol, aldol is going to leave you with the OH. Guess it's time to be done. I think. You can't quote me on that. I mean, you can quote me on that, but I may not be right. I would have to go through and look at the details of the actual mechanism, because it's not one that I can pull that cleanly out of my head. Okay. So with that, I'm going to stop the recording. Take